So Yunseo Choi from Harvard University is welcome to speak about the image of the pop operator on various lattices.
Yeah, thank you for the introduction. Just to lay a little bit more context, I am an undergrad at Harvard, and this was the research that I conducted as a part of the University of Minnesota Duluth research experience for undergraduate programs last summer. And so, yeah, I'll dive in right away. Okay, there we go. So the classical pop stack sorting map takes a permutation of length n and acts by reversing each descending run. And so, for example, if it takes the length 7 permutation 3, 7, 6, 1, 2, 5, 4, then it partitions the permutation into 4 descending runs and reverses each descending run. And a natural question that we can ask is whether we can generalize the classical pop stack sorting map. And to do so, we'll have to understand the classical pop stack sorting map through the lens of lattices. And so just to recall some preliminaries on lattices, recall that a lattice is a poset in which any two elements have a greatest lower bound and a least upper bound. And so, for example, a canonical example that's often mentioned with lattices are all subsets of A, B, and C ordered by inclusion. And in particular, a definition that's going to be relevant for our purposes is covering relations. And so for any two elements x and y, we say that x covers y if x is greater than y and there's no z in between x and y, such that y is less than z is less than x. And so, yeah, if we recall our classical example, then we can see that the set AC covers the set A because AC contains A, but there's no intermediary set in between. And in particular, as long as we have all the elements and the covering relations of a lattice, then we have the entire lattice well defined. And so, yeah, we can come back to our original question of how we can generalize the classical pop stack sorting map and refine our question by asking how we can generalize the classical pop stack sorting map, not just to any structures, but to lattices. And so Define in 2022 answered this question. And so what he did was for any element x, in order to define the pop operator, we take all the elements that x covers, and that's this first set up here, and then take the union with x, and then take their greatest lower bound. And in particular, this union with x in the end is just there so that when x doesn't cover anything, this first set will be an empty set. And so this is just here to make the function well defined. And so intuitively what it does is it looks at a element x, look at everything right underneath it, and then take all their greatest lower bound. And so, for example, if we were to apply the pop stack sorting operator, the generalized one, on our subsets of A, B, and C, then our x will just be the set A, B, and C. The second row will contain all elements that x covers. And if we take their greatest lower bound, then because none of A, B, or C appears in all three of these sets, we will have the empty set. And so if we apply the generalized pop stack sorting map to this lattice on A, B, and C, then we get the empty set. And so, yeah, now hopefully the generalized classical pop stack sorting map agree with the classical pop stack sorting map when we define some kind of lattice on S of n. And so there is a lattice called the weak A of n minus 1, which takes permutations of length n and say that a permutation x covers a permutation y if y is a result of reversing two adjacent numbers in x that are out of order. And by out of order, I mean the larger number is to the left of a smaller number. And so, for example, this is a structure of weak A2. And so, for example, if we look at this number 3, 2, 1, then there are two pairs of adjacent numbers that are out of order, namely 3, 2, and 2, 1. And so to get the set of elements that 3, 2, 1 covers, we can first reverse 2 and 3, and we have the 2, 3, 1 right here. Or we can also reverse 2 and 1 and have 3, 1, 2 right there. And so if we continue this chain eventually we'll have all the permutations of length 3, and this is what the lattice looks like. And so now, hopefully, the classical and the general pop stack sorting map agree when we take the lattice on the set of length n permutations to be weak A of n minus 1. And indeed it does. And so recall that the classical pop stack sorting map takes a permutation of length n and acts by reversing each descending run. And recall that this is a generalized definition of pop stack sorting map, where you take an element, look at all the things it covers, and then take their greatest lower bound. And so we can ask why the two are equivalent when M is weak of A of M minus 1. And so recall that in weak of A of M minus 1, we say that X covers Y if Y is a result of reversing two adjacent numbers in X that are out of order. And so if we apply the generalized pop stack sorting map, then in any one of the permutation, in some permutation that X covers, if we look at any two numbers that are currently out of order, that belongs to the same descending run. In some permutation that X covers, the two numbers will be in the correct order. And so if we take the greatest lower bound of all of these permutations, because every two pairs of orders that were adjacent to each other that were out of order initially must be in order, every descending run must be reversed. And so we can see that in this case, the two definitions agree as we would hope to. And now that we have this function defined, a natural question we can ask is how we can study the image of the pop stack sorting operator. And so Defon and Williams in 2021 defined the following generating function, where it's defined over the image of the pop stack sorting map. And we further refine the count by grouping those elements that belong to the image of the pop stack sorting operator by the number of elements that cover X. And so the reason why this is a natural generating function to think about is it has to do with labeling the edges of lattices with joint irreducibles. And Q in particular here keeps track of the dimension of the facets, but that's a little bit out of the scope of the present talk today. But in particular, even just taking Q equals 1, we can see that the generating function returns the size of the image of the pop stack sorting operator. And so even this was an open question for many of the lattices that I will soon talk about. And so yeah, in addition to defining this generating function, Defon and Williams conjectured that the generating function takes the following form for the following 6 lattices. And since then, all of these problems have been solved. Hong in 2021 was the first to solve the first conjecture. Myself and my collaborator Nathan Sun have proved the middle 4 conjectures. And most recently, Bernard, Defon, and Hansen proved the last conjecture. And so yeah, just a little bit more into one of the lattices, this Tomori B of N lattice. I can't walk through every step of the proof, but I'll just give you an idea about what this lattice is and what kind of steps that we took to arrive at this result. And so yeah, we first have to define the Tomori B of N lattice, and it was originally defined by Thomas in 2003. And so it is a sublattice of weak A of 2n minus 1. And so it is a sublattice of the lattice that takes like 2n permutation, and then with the covering relation given by reversing elements that are currently out of order. Yeah, and so with that, it suffices to just define what the elements of this Tomori B of N lattice are. And so there are permutations of length 2n for which the ith number and the ith number from the left and the ith number from the right should sum to 2n plus 1. And also, there must be no subsequence that is order isomorphic to 3, 1, 2, in which the rightmost element, the xc3, is greater than or equal to n plus 1. And so this might seem like very arbitrary conditions put it this way, but the motivation comes from triangulations of 2n plus 2 gons that are fixed under half turns if we label the 2n plus n gons with 1 and 1 bar and so on. Yeah, so for example, in Tomori B of 3, we see that 4, 1, 2, 5, 6, 3 belongs to Tomori B of 3 because, well, for one, we can see that if we sum the first number and the last number, the sum is 7. 1 plus 6 is also 7. 2 plus 5 is also 7. So it satisfies the first condition. And we can also, you can stare at this permutation and convince yourself that there's no subsequence that is order isomorphic to 3, 1, 2, and also one for which the last element is greater than or equal to n plus 1, in which our case it would be 3, or 4, n plus 1 would be. On the other hand, we can see that this other permutation, 6, 2, 3, 4, 5, 1, does not belong to Tomori B of 3, because even though it satisfies the first condition, we can see that the subsequence 6, 2, 5 is order isomorphic to 3, 1, 2, and also this 5 is greater than or equal to n plus 1, in which our case is 4. And so yeah, this is what the Tomori B of 3 looks like. And one particular thing that you can notice is that in the week A of 2n minus 1, in the entire lattice, there will be a lot of permutations in between 6, 5, 4, 3, 2, 1 and 3, 2, 1, 6, 5, 4, because a lot of the numbers that were out of order in 6, 5, 4, 3, 2, 1 are currently in order in 3, 2, 1, 6, 5, 4. But because we're taking a sublattice, a lot of the elements in between have disappeared. And so, yeah, one thing that's important for us is this notion of half k of x. And so we define the half k of x to be the kth maximal substring from the left that contains a number that are at least n plus 1. And so, for example, if we take the permutation 4, 5, 1, 6, 2, 3, then the numbers that are greater than 4 are 4, 5, and 6, but 4, 5 appears right next to each other. And so half 1 will be 4, 5, and half 2 will be 6. And then also we're going to define the notion of reduction, which is we take a permutation and replace it by the ith smallest number in x with I for all I. And so, for example, in our permutation 4, 5, because 4 is the smallest number and 5 is the next biggest number, we make that 1, 2. But simply in the case of half 2, when the half 2 just returns to 6, it just happens to be 1. Yeah, so this is a theorem that we ended up proving. And so to sketch the proof, a priori, it's not even clear, although it's known, what the pop stack operator does. In the classical case of week A of 2n minus 1, we know that it simply reverses each descending run. But a priori, it's not even clear what exactly the pop stack sorting operator does to the permutation itself, although this has been known and has been studied before. So yeah, those are some kind of challenges in between. But we first showed an if and only if statement, which says that a permutation that is already in Tomori B of n lies in the image if and only if 1 appears to the left of 2n in x. And each of these reduced half kx is in the image of the Tomori A of n lattice, which was the first proof that Hong gave in 2021, the same conjecture. Yeah, and so once we have this exact characterization, we used a generating function to enumerate this sequence. And so, yeah, that's it. If you have any questions, I'd be happy to answer.